Okay, so couple of announcements. Remember right after class today is the CS get together. I think it's happening right out in here. So good prizes, fun, lunch, blah blah blah. So make sure you at least hang out there for a little bit. It's a good way to get to meet other, CS people. Also tonight we have a tech talk. Aiden might be coming by to also remind you, but I think it's at 6 o'clock. 6 to 8 probably is how it's scheduled. Usually it lasts for an hour or something like that. So this week it is Eric Johnson from Aurora WDC in Madison, who's one of the companies that does a lot of our internships. Raquel here is interviewing with them right now for an internship. So these are like legitimately uh, real things. So I would encourage you to show up to that. It's here on campus. I assume down in the makers, like by the Makerspace business building, or is it here in CS? See it here in CS. That might be true since we had the last time they were here. Actually one time he did it out in the bluff during COVID. But anyways, that's a good one to go to. They're a company that does, if I've never mentioned them before, they do business analytics, applying AI to like business decisions for where a company should spend their next dollar. So cool type of application, very forward thinking. That would be a good company to create a relationship with. They have hired several of our former students full time. I think they probably have like 7 or 8 former Concordia CS students who work there full time. And then every summer, they usually have 3 or 4 interns, something in that ballpark. So I encourage you to take advantage of that. Okay, so let's dive into our plan for our Connect 4 game. So we're going to focus on the code side here for a little bit. And then we will come back and catch the interface up. I'll probably offline build my board um, rather than go through that thing again. You kind of saw the starting place for my stupid board. But let's build the behind the scenes thing. So again, what we're doing here is we're kind of seeing the model of building graphic user interface applications, whether it's games, whether it's business applications. It's not a new way of coding. You still have that behind the scenes. A lot of times we call it the back end side of your code. So we're going to have normal back end code that's driving the Connect 4 game. Just instead of driving a text-based user interface, we're going to be connecting it to our Unity application for there to be a visual aspect of our game. Okay, but really the logic under the hood is the same. Okay, so last time we started talking about this, where we're going to need some objects. We're going to need a board, and a board is going to be a collection of checkers. So a board's going to manage a two-dimensional array. We talked about this last time, the idea of two-dimensional arrays. It'll be a two-dimensional array of checkers, where there's 6 rows and 7 columns. We then probably will have something like a game manager or something like that that effectively has the board and plays the game back and forth between 2 players. Probably initially, what we'll do is we'll have 1 player, and then we'll have a crappy AI that is making the decisions. If you want to, maybe we'll look at ways to make the decisions a little bit smarter. So we could have I mean, we say AI, but in many cases, it's not going to be doing anything amazingly AI-ish. It's just going to be maybe looking at the board and seeing, are there any Connect 3s that could become Connect 4s on the next turn? Um, that would be a pretty hard AI to beat at that point, because that's kind of the point of Connect 4 is, as a human being, we tend to sometimes miss things because it gets all jumbled up into all the squares. So, all right. So for a checker, maybe initially a checker just has color. So let's design it here first. Next semester, many of you will be taking the software engineering class, right? So one of the things you're going to run into in the software engineering class is that you'll spend less time coding and more time planning. And if you plan well enough, then in the end, your code kind of writes itself. And this concept is actually something that is very related to current trends with like AI-based programming, where we're using tools to help us generate code. we need to be able to articulate clearly enough to the whatever AI model we're working with, the requirements of our application so that it can generate the grunt coding for us. But what the skill set is going to be able to articulate the requirements. That's software engineering. So software engineering, only the very final step is the idea of actually writing the code. And I know it seems boring, but the idea is it's a more efficient way of writing code correctly first. It also lends itself to working in a team. Kind of the modern day way of team-based software development is something called Agile. You'll learn about that in that class. You do these things like sprints and stuff like that, where you kind of get assigned this one little pod of work. And you get to implement it however you want it to implement, but the rules are it has to have these inputs and these outputs so that whatever your thing does, it feeds into the next guy's thing. So you don't have to worry about different pieces. Most employers are going to work with agile software development. Aurora WDC uses Agile. Yeah. So in any case, let's start designing our objects here. So we're going to have the idea of a checker. And at the very least, a checker is going to have, we can have it have a color. We can have it just have a type, either a 0 or a 1. We can kind of decide. For right now, let's just keep it in line with what Connect 4 actually looks like and say we're going to do it as a color. So we're going to have a string color. And that's all a checker is going to have initially. All right, so before we go any further, let's go and write this, just so we can kind of see these things come alive. So I'll jump over here to Unity. I think I already have my project running here. I'm in my assets folder. I'm going to go ahead. I don't have a scripts folder yet, so I'll create a new folder for scripts. And then, like I did before, I'm going to create a subfolder in here for just normal classes as opposed to mono behaviors. So our back end is likely going to be a whole bunch of normal C# classes to represent the various things in our game, and then our mono behaviors will be the thing that operates off of those, plays the game, and then makes it visually appealing to us. All right, so I'm going to create a folder in here called classes. Go in there, and then I'm going to create a mono behavior script. That way it gets associated with the project correctly, but we're going to very quickly make it not a mono behavior script. And let's call this guy a checker. Go ahead and double click on that. Do that later. Do that later. Increase the font here. That big enough font? All right. So right off the bat, we're going to unmono behavior this dude, which means he will no longer have a start and update. Instead, we're going to have our constructor for this guy. Let's see what this guy thinks a checker should be. All right, so inside here, we're going to have a private string color for the color of our checker. We'll have a public checker. It'll take in the string for color and set the color equal to that. And we could also go ahead and give ourselves a get color to have a checker have the ability to hand us its color as a read-only type thing. So we made it private here, so it's only accessible inside the checker class. And now get color allows us to get read-only access to that. That's our checker. All right. Probably going to add some stuff to it later, but this is what our checker is going to be. All right. Questions on that? All right. So we're kind of growing this thing from scratch. Go back into here. What's our next thing? We're going to need a board. All right. So let's go ahead and add a board. Let's actually call it a Connect 4 board. So we're specifying the kind of board this guy is. So this guy is going to be a two-dimensional array, 6 rows by 7 columns of checkers. Start off with just that concept. All right, so let's go and create our Connect 4 board. Here. So inside of my classes folder, I'll right click. I'm going to create mono behavior. We'll call this guy Connect 4 board. Go ahead and open that dude. All right, unmono behavior it. And we're going to have a private checker. I like to call it like the board for no good reason. That just seems to be my habit. And then we'll have our Connect 4 board here. This guy is going to be a, oh, actually, this will go along the lines with what we looked at last time. Actually, I'm going to do it so we can talk about it this way. All right, so this dot the board is going to be a new two-dimensional array of checkers. And I actually think the syntax for C# is something like that for array. We'll come back and get the correct syntax here shortly. Looks like it put it in there. Do we just fill it up with whatever? All right, so we'll create our two-dimensional array for our board. It's going to have 6 rows, and even though we aren't putting the number of columns here, what we're doing is we're going through and we're filling it up with an array of arrays, which is what we talked about last time. We go back to our slides here, and we were looking at what is a two-dimensional array, something like this, an array with 6 rows, 7 columns. This would be the syntax in Java, very similar in C#. But in any case, what it does is it creates an array. That's a one-dimensional array with each bucket containing an array. All right. So what we're doing here in our code is we are going through all the rows in our board, and we could have replaced 6 with the board dot, I think it's board dot size. This dot, the board dot size. Is it length? It is length. So this dot, the board dot length, that'll come out to be 6. So it allows us to generically change how complex our board is, I guess. So it's going to go through every element of our one-dimensional array, that is the board. And for each of those elements, it's going to create an array of 7 checkers. All right. Now, when we get to line 15 here, or past line 13, the board is a collection of buckets capable of holding checkers. There aren't any checkers in there yet. Make some sense? All right, which is good because when the game of Connect 4 first starts, we have an empty board and the players each have a pile of checkers that they're feeding off of. We don't really need to keep track of how many checkers are left. I don't think. Does Connect 4, is the game like a draw if you run out of checkers, or is there an exact number of checkers? The red versus the black checkers add up to the exact number of moves that would fill the board. I think that's probably how it works. Okay, so we don't have to keep track in our game of if it's player 2's turn, is he out of checkers? We can just keep going until the board is filled. All right, so when we first create a Connect 4 board, that's all it's going to be, is a empty board filled up with 7 bucket arrays representing our columns with checkers. All right. Leave it at that point for right now. Let's not even build in the ability to get the board yet. We might have the board completely housed inside of Connect 4 board and then have our game master or whatever make requests to the board. So the board ultimately reports to us, is there a winner? something along those lines. All right, so the game master just handles whose turn it is and allows them to make a turn and then tells the board they would like to drop checker into this column. Then we'll check, is there a winner? So the logic we're going to be building is, what does it mean for there to be a winner? All right. Now we're going to go ahead and create our game master class just so we have it here, but we're not going to do a whole lot of stuff in there yet. We're going to focus here on the Connect 4 board for a little bit because this is ultimately the thing that's going to be mechanically manipulating this array. All right. So going back into our planning stage here, though, what did I call this guy? Game manager. So for game manager, we're going to have 2 players. We can decide the nature of those players later. So we'll have 2 players. Those players will take turns making moves. This will control an instance of board, Connect 4 board, right? And then manipulate the board to play the game and report to Unity what should happen with the game objects to always show the current state of the board. So more than likely, there's going to be a mono behavior that creates an instance of game manager and tells that guy to start playing. And game manager would then say, okay, well, we need a new checker game object. It's going to drop into column 4. It'll move it into position, let go of it. It'll grab it, it'll make it fall, and it'll make the visual move. But behind the scenes, our board gets updated logically. All right, so those are the 2 sides of our application, the front end and the back end. All right, so let's create our game manager script just so we have it. Go back into our classes, right click, this guy game manager. Mono behavior, that guy. Dump the contents. This guy is going to control a private Connect 4 board. Called the board. We'll have a public game manager that'll take nothing in as a parameter, and it will set the board equal to a new Connect 4 board. A new Connect 4 board, at least as of right now, doesn't require any parameters to build it. The constructor just says, okay, well, we know it's a 6x7 thing. We're going to make 6x7 buckets, each capable of holding a checker. Okay, so that's what we have there in our game manager. So let's go back to our Connect 4 board because this is the actual guy that's going to be making the move. All right. So in Connect 4, when we make a move, really what we're doing is we're selecting a column, 0 through 6 for 7 total columns. Which column are we going to be dropping the checker into? All right. So we probably are going to have, let's go ahead and add it to our requirements, just so we have kind of a documentation thing here for it. So Connect 4 is going to have a function make move that takes in a column number, and this guy tries to make a move on that column. And we say try. My brother used to cheat this way in Connect 4, where even if a column was completely filled, he'd try to balance the checker on top. My brother cheated at basically every single game. Is laser tag still a thing? I remember as a kid, we used to have a laser tag kit or set, and we had this giant evergreen in our front yard. I mean, maybe it was shorter than this, but from my perspective, this was like a 40-foot tree. I mean, tall. And my brother climbed all the way to the top of this thing, and we were shooting at him, and we must have hit him 5, 6 times as he was falling out of this tree, hitting every branch on the way down. All the sirens are going off. Davis said he was fine. Got up, turned it off, back on, said, "You missed me," ran off. This is my 8-year-old brother. And I've hated him ever since. All right. But now he's got revenge. He has 2 boys, and one of them's like him. All right. So we're going to have make move. And let's go ahead and write make move and think what needs to be in here. So we probably want make move to return a Boolean as to whether or not a move was successfully made, right? Because we're going to try to make a move. So we're going to have this guy be public bool make move. This guy will take in a column as a parameter. All right. So now we can do a couple of things initially. We first of all want to make sure they gave us a legal column. So that means it has to be greater than or equal to 0 and less than or equal to, in our case, 7. Okay, because those are the legal columns. Now, one thing we can do here, since we don't necessarily want to say, we don't necessarily want to hard code a 7. Hard coding is generally frowned upon, let's say. So what I'm going to do up top here is I'm going to add 2 more private variables. So we're going to have a private int rows, and we're going to set that to 6, and a private int column, set that equal to 7. So then down here, we're going to say this dot rows for a number of rows for our 2-dimensional array. And it's the same thing as saying 6 right now, but it allows us to say we want to invent a new style, Connect 4 board that has 300 rows by 1,000 columns or something like that. And let's just go. See what happens. Probably want to have 2 computer players playing that one. And it's, instead of Connect 4, it's like Connect 30 or something like that. All right. So our board will be an array of some number of rows, whatever's represented by this variable up here. And then our number of columns will be this guy right here, this dot columns, which right now is 7. All right, so we really haven't changed the semantics of this. We've just made it generic so we can change this in 2 places and have it work everywhere else. All right, good programming practice, we would probably call that. Now, under make move, we want to find out, is this a legal move? So let's go ahead, and we can do this different ways, but let's just try to disqualify it as a move through several if statements initially. So if column is less than 0, or column is greater than or equal to, this says this dot columns, but that's actually an error, right? So this should be greater than or equal to the number of, well, actually be greater than this dot columns minus 1. Because if it's less than 0 or it's bigger than 6, this dot columns is currently 7. The legal columns are 0 to 6, right? So 7 columns, since it's an array is 0 index, the legal columns are 0, 1, 2, 3, 4, 5, 6. So if they try to give us a column that's less than 0 or a column that's bigger than 6, we're going to say this is an invalid column. We'll just return false. We did not make the move. Good enough? All right. So that's the first check there. Now we need to make a check to make sure that is the column they picked, does it have is that a legal move? That is, my brother David, is he not playing where he's trying to balance a checker on top of the thing? So we need to make sure that in our case, row 0, because kind of from our perspective, our board is like laying upside down. The first row is actually the row at the top. So if we look at our picture here, this is, let me, to steal those, just move them over here. We'll change that to that color. This is 0, 1, 2, 3, 4, 5, and 6. I'm going to go ahead and replace my fake memory addresses I put in here with indexes. So this is 0, 1, although we didn't actually do 7 columns, did we? Well, whatever. 2, 3, 4, 5. Then we need one more. That's 6. And this will be memory address 134. Why is our memory addresses here? Why do they go from assuming the base address of AR is 100? Why do we go from 100 to 106 to 112 to 118? I'm not doing good math here, am I? This is by 6. That's by 6. That's by 6. That's by 6. That's by 6. So this would be 136. So why are we doing jumps by 6? Yep, exactly. Addresses are 6 bytes long. Again, that's making an assumption how the modern operating systems typically work with 64-bit memory managers. Usually only 48 bits are available to the user. So we're inventing how big these memory addresses are. As a programmer, we don't necessarily need to worry about that. That's managed for us by the language and the operating system working together. This is just showing us, really in this example, that arrays are written with contiguous memory in mind. These are buckets right next to each other, and they need to be big enough to hold the values that live in those buckets. And what value lives in each of these buckets? Well, in each of these buckets is a memory address. Why is it a memory address? From our code right here, it's a memory address because we are creating a new 7-element array for that guy. All right. So that's why we have all those memory addresses there. Thing here is the new keyword should scream to us we're probably dealing with memory. So whatever we're putting right here, it has to be big enough to hold a memory address, however big that is. We don't have to know that it's 6 bytes or 8 bytes or 1,000 bytes. Doesn't matter. It's the size of a memory address on whatever operating system you're currently on, and the language takes care of it for you. Okay, so when we make move, we'll pick our column. We'll first check, is the column completely illegal? Secondly, we want to ask the question, is the column, if we're still kicking here, I kind of think about this as like creating a minefield. If we're still kicking right here, it means that at the very least, they gave us a legal column that might be able to have a fair move. So now how do we check to make sure that whatever column they picked can take at least one more checker? How do we ask that question? Well, first of all, how do we talk about the column? If we're still alive here, we know that the column they've given us is actually going to go, don't show me this. All right, it's going to say, here's our board. Let's just go ahead and look at row 0. Row 0 is the top of our board from our perspective, right? And if there's already a checker in that location, that means that there's no room to put any more checkers in there, right? So if the board at bucket 0, row 0, at column, whatever column they passed in, which we know right now is legal because we're still alive after this if statement. So remember, the return keyword makes a function immediately end and potentially return a value. In this case, it does because we have advertised we're going to return a Boolean. All right. But the important thing is if we got inside this if statement, we would not still be alive right here. All right. So if we're still alive right here, at the very least, they gave us a column between 0 and 6. So now we're going to look at row 0 and look at whatever column they gave us. And if it's something other than null, that means there is already a checker there. Null means there's no checker there. So if it's something other than null, we could ask it whether it's an instance of checker, but we know that we're only putting checkers into this guy. We might end up using an inheritance model where we have a baseline checker and then we have red checkers and black checkers. We'll get to that when we get to it. But as long as it's something other than null, this is that we have an opening, at least one opening for a checker. All right. So if it is null, return false because this column is full. Make sense? All right. So far, AI is getting like well, maybe a B plus and did screw up here. So again, word of warning. I guess AI can help you with debugging skills, but if you rely on it too much and do too much at once, you can get down some bad paths. All right. So if we are still alive here, that means we have a legal move and room for a new checker. So drop the checker onto the board. What does that mean, to drop the checker onto the board? We know we have at least one open spot, but we might have 5, right? Or 6. This column might be completely empty currently. So if we know we can drop it into that column, we know we're going to ultimately get a return true here, right? The move is ultimately going to get made accurately. So we can go ahead and throw that guy in here. Let's see how AI did on this one. All right. So what we're going to do is we're going to find out where is the farthest down that we can drop this checker. So it looks like this is doing at least mostly, right? So we'll start at the very, very, very last row. Keep going as long as I is greater than or equal to 0. So we'll start at the very bottom row and work our way back towards the top, subtracting 1 each time. So we'll go from row 5 to 4 to 3 to 2 to 1 to 0. We know that at the very least we can put it in 0. All right. But we want to find out how far down can we put this guy. So we'll ask the question, if the board in the row we're currently looking at the column that we already know is legal, if that is equal to null, that means we have an open place to put this. Go ahead.
Why is that? Oh, never mind.
Okay. I wonder if is there a way to turn off just like the front light? Probably will let you see it better, wouldn't it? There's like a switch thing, but does it have multiple buttons on it? Just start pushing them randomly. Or just turn off all the lights. It can't be that dark in here. Yeah, they're just dimmed. Oh, is this more? Oh, look at this. Okay. Oh, we good? I didn't touch anything. Are we good? Is it better? Extra good? All right, good. I feel like I would not have been very good at that. So, well, I would have just kept banging on buttons. All right, so somebody, is that a lot easier to see? All right, so somebody remember to do that every class. I have bad eyesight anyway, so I don't need to see what's going on here. I grew up with those CRT monitors. And if you've ever seen those in a movie or a TV show, what do you see? You see those lines scrolling down the screen. You don't see it in real life, but your eye muscles do. So I have like no focusing muscles in my eyes from staring at those for zillions of hours when I was younger. So you just blink a bunch of times until things come into focus. All right. So we're trying to figure out how far down in our rows can we actually place this checker. So we'll start at the very bottom row, work our way towards the top. If the row we're currently looking at is equal to null, that means we have found the farthest place down that we can actually place a checker. All right. And So we'll go ahead and place the checker. So the board at row I, column, whichever one we've put in there that we know is legal, is going to be a new checker. Right now, we're just putting in the color red, just so we can work with this. When we make a move, let's make a move with the column and also the color. And then we can update this guy to be the color that was passed in. So we expanded our make move function to now take two pieces of information. What column are we trying to drop this into, and what color should the checker be if we can successfully drop into that column? So far, so good. All right. So legal column, yes. Is there still room in that column? Yes. Let's find out how far down we can drop the checker before it finally hits. So effectively, what we're doing here is we're programmatically handling what should happen in our game once we've been building up our thing when we just hover a checker above that column and let go. Gravity is going to let it fall as far as it can fall. We are programmatically figuring out how far will it end up to make sure our board matches this, and then we'll just let gravity do the rest of the work for us. Hence the value of a physics engine. All right. So if we're looking at an empty spot by starting at the farthest down row, then we'll go ahead and place the checker with whatever color we were trying to place. We'll break out of our loop, which gets us out of our most local loop, and then we'll return true. Now, technically, we didn't even need to break. We could have just returned true, but let me test you here. Why is that going to be a problem? Why is that compile time that's going to scream at us? Here is the entire function. Everything you need to answer this question is found here. So in fact, we see the little red squiggly. I'm just not going to hover over that. Hopefully it didn't put it somewhere else on here. Go ahead. Nothing gets returned. So we're dealing with a strongly typed language. This goes back to week 1 or week 2 of CSC 2000, right? For coding 1, where we talked about the different types of programming languages. We are working with a strongly typed language. Strongly typed languages require us to advertise the types of values we're dealing with. This happens at the time when we're creating variables. It also happens at the time when we're returning values. All right. So if we advertise we're going to return a Boolean, we better return a Boolean. Okay. And as he pointed out, because we only return this true value, well, we return false if we get into this if statement. We return false if we get into this if statement. We return true if we get into this if statement. Now we know, because of the logic we've written here, we know we will end up inside of one of these if statements because we know the problem we're solving. But the programming language here doesn't have that level of intelligence behind it, right? It sees these 3 if statements as only possibilities. You might only maybe get into those. So there is a chance here that this code never returns a value, which it's going to have a problem with. All right. So if we hover over that error, it's going to say not all code paths return a value. Pretty straightforward error. So, but there's also, again, a reminder when you get errors in your code, don't just randomly start changing crap. Look at the error, maybe say it out loud, try to figure out what you think it means. One of the skills you build as a programmer over time is the ability to debug. In fact, it's probably a more important skill than I don't know, the logic of it. I think logic is easier than the debugging, because debugging, you may have made a mistake that you weren't even thinking about. And if you just start randomly changing stuff, who knows what else you're breaking. This also goes into another software engineering concept that you'll learn in that course with something called unit testing and also regression testing. So basically, when you create applications, we don't do it in our applications here in class because the applications are relatively small in the big scheme of things. But also they're kind of throwaway applications. We're probably not throwing these on the App Store where whenever we make upgrades, we need to make sure it still works. But the idea with unit tests is you create a section of test cases that your code needs to pass. And as soon as somebody points out a bug in your program, you fix that bug and then you add a test case for that to make sure that works. So that whenever you make a change to your program, before you release it as the next version, you run all the former tests to make sure it still passes all the hoops and you didn't introduce at least a previously known problem. Does that make sense? So that makes testing of your code easy. What we do here is kind of fly by the seat of our pants and just say, okay, we wrote some stuff. Let's test it a couple things. We do one or two tests and we say, okay, it obviously works for everything. And, and then we move on. But in any case, yeah, be a good programmer. Do as I say, not as I do. I don't play well with others, so I tend to not write software in teams. All right. So we need to go and patch this up. We can just go back to our previous version where once we find a place to put it, we know we're getting into this if statement. At that point in time, we'll break out of this loop so we don't try to place more than one checker, right? If we forget to break out here, then all of a sudden we're going to get a stack of checkers. One move becomes an awesome ninja move with an instant connect 5 or 6, depending on how far down the thing we go. We only want to place one checker as far down the column as we possibly can go. So as soon as we've done that, we'll go ahead and break out of this loop. And this line right here, line 39, is guaranteed to get hit in this function. We know by the time we get here, a checker has been placed. C#'s compiler here can just confidently say, I don't care what has happened, every single path in your function returns either true or false. When this guy ends, he now has returned a value. We should see our red squiggly is gone. Everybody's happy. That's a move. All right. Questions about that? That's the whole connect 4 ninja move thingy. All right. Not too bad. And we saw if we relied on AI to write that, we would have had a couple of zigs and zags. It's always those. It's always the minus ones or the plus ones that you run into problems. Null pointer exceptions or whatever C#'s equivalent is. Array index out of bounds exceptions is the Java version. Those right off the bat, when you're debugging it, should scream, I've walked off the end of an array. Whether it's rows, whether it's columns, I have stepped onto land that I don't own. Therefore, I need to go back and check my counters. I've gone one bucket too far. Make that error enough times, you will either stop making the error or at least you'll know where to look right away. All right, so now we have the ability to make moves. The next ability we're going to have to create is the ability to check if there's a winner. Yeah, it comes in as a parameter to the function. Yep. So the next thing we want to do is we want to check, was there a winner? So let's see where we're at here. So this is in our connect 4 board. We're going to have another function called isWinner. And this guy doesn't have to take in any parameters. Realistically, we would call this immediately following making a move, successfully making a move. That means we called our make move function and we got a true out of it. Checker has been dropped because only after a move has been made is there a possibility that we now have a winner, right? All right, so isWinner function returns true if there is now a connect 4 somewhere on the board, and false if there is not a winner yet. Make some sense? All right. I would encourage you to think about the logic for this. The main reason I'm not giving it to you as an assignment is we don't have a kind of a running program yet. So you might spend just as much time getting yourself set up with a test case as you would writing the code. So if you want to challenge yourself to go ahead and write is winner for next class, I'd encourage you to do that, to think through that process of, is there 4 in a row horizontally? Is there 4 in a row vertically? Is there 4 in a row diagonally? Okay. The diagonally obviously is probably going to be the most difficult of those. But effectively, you're working with this code right here, which I will give you. I'll go ahead and push my scripts folder up to GitHub, and I'll put on Slack the link to my thing, so you can look at my code as a starting point. But I already reminded them, but you can remind them again. Yeah. 6 p.m. in here. Okay, in the CS area here. Okay, got it. All right. Yep. So anyways, I'll give you a link to my scripts folder so you can see the code we wrote from class today. If you want to bring your project up to date with these things and debug it, that's fine. I won't put it as an official assignment because I don't want you to stress yourself out just getting a game running. Probably over the weekend, we will have something for the kind of the next step. But for now, questions, comments, concerns, bribes. Go ahead. Yeah, I'm purposely on GitHub, just linking my scripts folder, because when you link the entire Unity project, it becomes kind of large, and then also GitHub starts complaining about having to use their large file system. It's completely doable, but it doesn't really gain us anything in here since we're focused on the code. But yeah, I'm going to give you a GitHub link to a scripts folder that has all our scripts in it. Other questions, comments, concerns? All right, don't forget about the CS get together right outside the door here. And I will see everybody on Friday. Sure.
I wanted to make my